Hello everyone, thank you for being here today. My name is Dr. Luna Zagorac, and today I will be telling you about ultralight dark matter and simulations, a chapel-powered eigenstate perspective. Now, first, I will motivate what dark matter is, and in particular what ultralight dark matter is and why we care. Next, I will introduce our chapel-powered ultralight dark matter solver, chplUltra. After that, I will tell you about how to calculate the eigenstates of a dark matter halo, what that means, and how that's powering our research, all with the help of Chapel. And finally, I will end on some conclusions and next steps. So first off, what is dark matter? Dark matter is this mysterious substance out there in the universe. It is about 5 to 6 times more. There's 5 to 6 times more of it than our regular matter that makes up things like the Milky Way that you see here. So this is something that our Milky Way might look like, and this is about where we are. So wave high to our home. That's where the solar system is. That's where you and I are right now. And this Milky Way, or this any galaxy that we can see through telescopes and by taking pictures and stuff, is surrounded by something that we can't see, a halo of sorts. So here we have the shiny, pretty galaxy, which is made up of so-called regular matter or baryons. So these are things like stars and galaxies and planets and you and me and chairs and stuff like that. And around it is a halo made up of something called dark matter. So dark matter is this mass that exists in the universe that we can't see. So we know that it's there because it interacts gravitationally, but we can't, see it through a telescope the same way that we could this galaxy. And so what exactly dark matter is made of is one of the big questions of 21st century physics and astronomy. And one way to get at that is to model these dark matter halos that exist around galaxies, particularly using numerical solutions. So in particular, we are interested in one possible explanation, which is called ultralight dark matter. So ultralight dark matter is an axion-like scalar boson, which is physics speak that says this is a particle that likes to cluster. They like to be in a group together. It has extremely low mass, 10 to the minus 22 electron volts. And if electron volts are not your preferred everyday unit of measuring mass, suffice it to say that comparing the mass of this particle to an electron, an already extremely small particle, is like comparing said electron to a tennis ball. So it's incredibly, incredibly light, which means that we have a lot of these particles making up a dark matter halo around, say, our galaxy. And what is particularly interesting about this particle is how it likes to arrange itself in a halo around a galaxy. So if you look at this very expertly drawn sketch here on the right, what we are showing is the density of dark matter as a function of radial distance from the center of the halo, or the center of the galaxy equivalently. And here in the black, we are showing the profile, the radial profile of what this might look like for ultralight dark matter. So on the left, where the radial distance from the center is smaller, we see this core, this bump, that is also called a soliton, which just so happens to correspond to the ground state of the system. More on this later. And as R grows, we see that it fans out into this skirt. This is in contrast with some other dark matter candidates, which form a halo sort of more similar to what you see in the gray here, meaning that they form a cusp at this point as R goes to 0. That basically hints at infinite densities at the center of the halo. We don't like this. Infinite densities aren't very physical, and so we are much happier with this core that is formed by ultralight dark matter, and this is called the core cusp problem. Our candidate also helps with some other smaller problems in cosmology, but mainly it behaves in a really, really cool way, which means it has really cool phenomenology. And in order to sort of track how it behaves, we need to simulate it, ideally using Chapel. Before I can tell you about that, I will introduce the set of equations that we use to simulate ultra-dark matter. So the first equation here is the Schrödinger equation, which tells us how the probability density of how these particles like to be arranged, called psi, evolves with time. So on the left, we have the time derivative of psi, and on the right, we have two terms, one of which depends on the Laplacian of psi, and one of which depends on psi times this parameter called phi. Phi here is the gravitational potential of the dark matter, because remember, it has mass, it just doesn't know about light. And how this gravitational potential evolves is shown in the second equation here, called the Poisson equation. On the left, we again have the Laplacian of phi, and on the right, we have four constants, 4, pi, g, and ma, where ma is the mass of the particle, or the mass of the axion, as we call it, times the absolute value of psi squared. Finally, probability density isn't something that you see when you look through a telescope and take data. So instead, we like to transform it into a mass density, which we do by multiplying the absolute value of psi squared by the mass of the particle and getting the mass density rho. If you weren't sure that you followed this, that's not a problem. There are two main takeaways that I want you to take from these set of equations. Number one is that when solving these equations numerically, the Laplacians, the del squareds, are the most numerically expensive to solve. This is where CHPL can help us. And secondly, due to the presence of the Schrödinger equation, we can calculate the eigenstates of the system under certain assumptions. So I will continue to tell you about one in this section, and we will touch on two in the next one. So the original implementation of the algorithm that we now use is in CHIUW, a code developed at the University of Auckland by Professor Richard Easter's group. It relies on using Fourier transforms to solve those pesky Laplacians and make them faster, or make solving them faster rather. And particularly it relies on wrappers for the C library, the fastest Fourier transform of the West, or FFTW, in Python. It demonstrates excellent numerical stability. It is parallelized but not distributed, which makes it really great for use on a personal computer. So for instance, on my laptop here, so I could run grids of say 64 cubed, 128 cubed, maybe 256 cubed, if I were interested in systems like that. And it's very nice and editable, and has a nice interface through a Jupyter notebook. So CHPL is still very much being used for research. However, for our purposes, we wanted to run finer grids, say 512 cubed or 24 cubed or something like that. And for that, we turn to CHPL. So we use almost the same algorithm as CHPL, and we rely on a CHPL-based distributed fast Fourier transform built in a 1D FFTW. Again, we show excellent numerical stability. We are parallelized and distributed, which makes chplUltra great for HPC use. And this is what helps us utilize CHPL's native abilities and get our code to run faster and to run larger grids. If you're interested in more of the details of chplUltra, I won't be going to them here due to the constraint of time. However, you can see Nikhil's presentation on simulating ultralight dark matter in CHPL at Supercomputing 19 at the PA workshop. If you Google this phrase, simulating ultralight dark matter in CHPL, you are sure to find the extended abstract and probably the slides as well. So with that, what does a halo made in chplUltra look like? Well, it looks a little bit something like this. I will explain as this GIF loops around. So this is actual data produced with chplUltra and a 512 cubed grid. So what we are seeing here is two blobs of dark matter, it doesn't matter what they are for our purposes, that merge in the center to form this halo-like structure. What you're not seeing here, since this is a slice through the middle of my box in one dimension, is two other blobs that hit the center of the halo in a perpendicular direction, sort of halfway through. And so once these things merge, you see something that looks like an example of a halo here. So the yellow center at the center of the box, that is the core that we like to see, sort of the bump at the center that is very characteristic of this dark matter candidate. And the little purple wiggles are characteristic of these interference fringes that we get due to the presence of the Schrödinger equation that make the skirt of our halo kind of like turbulent and interesting. So this is bona fide data that we are using to do science, and this is what an output from chplUltra might look like. So now that we have simulated a halo, we want to take a look at its eigenstates. But recall that I said that we do have to make one key assumption. So here, what I am showing you is the spherically averaged density profiles of the run that I just showed you in chplUltra. And I'm showing you those density profiles for about the last 30% of the simulation or so. So here in the colors, I've plotted instantaneous profiles at different times for the last third of the simulation. The colors here don't signify anything. They're just pretty. And the average of all of these profiles is shown in the black. And the takeaway here is that number one, this black profile and any of the individual profiles really looks like what we expect an ultralight dark matter profile to look like. We see this bump at the center and this skirt outside. So that's number one. And number two, none of these instantaneous profiles stray too far away from this average profile, that this black line is a pretty good approximation for this at basically all times. This means our halo, like our average halo shape, doesn't change that much. That means its average gravitational potential doesn't change that much. And basically that means that we can decouple the Schrödinger equation from the Poisson equation and just think about the eigenstates of the Schrödinger equation, which we know how to do. Doing that, we find that our eigenstates are nicely split into a radial component called F and a spherical component here, YLM. Our eigenstates here are psi NLM, where NLM are some quantum indices that I won't be getting into. So the radial component we solve using Mathematica, because Mathematica is very good at doing the linear algebra that I do not want to do by hand. And this is explained in detail in our publication of this archive number. So if you happen to be interested, stop on by and take a look. But this is what these radial profiles look like for one halo for a choice of N and L. So these really depend on the individual halo that we're simulating, on the mass in it, the shape of it, everything. However, the spherical components do not, which means that they're really, really good for which means that chplUltra is really good for using it to decompose our save files into the spherical coordinates by calling onto the GNU library of GSL spherical harmonic code. This is a chplC interface, which then runs in parallel. So the spherical harmonics are shapes that we already know. chplUltra not only decomposes our results into these individual eigenstates quickly due to its parallelization, it also saves us the hassle of having to write complicated mathematical equations by hand by calling on this GSL spherical harmonic code, which is great. Finally, an example of what this means in terms of physics research and how it's useful. So here, what I'm showing is the contribution of just the ground state squared on the left. This is equivalent to the relative mass of the ground state to the whole system. And the ground state just corresponds to that core that we are so interested in. So the question we're answering here is, how big is the core relative to the size of the halo in these different halos? And the colors here show how we made a halo by the collision of how many blobs. So the growing number n is equivalent to a growing mass because, colliding 8 blobs of equal mass will give you more mass than colliding 2 blobs of equal mass. And so we can see that, and in the late stages, so after about 0.2 code units which, in time, which everything here is in some internal code units, we can see that as the mass gets higher, as the number gets higher, the percentage of the mass of the whole halo that is in the core decreases. So this is interesting because it allows us to make predictions on how big of a core of a given halo out there in the astronomical wild might be, and this is helpful for looking for these cores, which are sort of one of the smoking gun signatures of this dark matter candidate. So with that, let me draw some conclusions. So dark matter, it's mysterious and it's everywhere, but robust computational modeling can help. We evolve our halos with chplUltra, which is fast and efficient thanks to chplUltra's FFT routines and the HPC friendliness of chplUltra in general. And finally, the eigenstates of ULDM halos are a new approach for gleaning sort of insight into this popular proposed dark matter candidate, and it is all chplUltra powered, which is the direction in which we're heading with chplUltra and our research. So thank you very much for listening. I'm going to ask for questions, though I won't be there in person to answer questions. Nikhil will be, but if you would like to ask me anything in particular, please feel free to shoot me an email. I would love to chat. Thanks so much, and I hope you enjoyed.